Very good afternoon. We'll see about waveguides unit of transmission lines and RF system design subject. So the waveguide definition is nothing but electromagnetic waves which is being guided between the two parallel plates. The two parallel plates are imagined to be of conducting one. It is being kept in the x direction. And the plate regarding the y and z direction will be considered to be infinite. Be considered to be infinite. Let us see the diagram of it. The two parallel plates which is kept at x equal to 0 and x equal to a. Between the two parallel plates, we will assume the waveform to travel. And for that we'll first assume the Maxwell's equation of two kinds, that is one is related to the H and the other one related to electric field, that is del cross E. First one is related to del cross H. The equation is given by j omega epsilon into E, and del cross E is given by minus j into omega into mu into H. So del cross H and del cross E can be written in terms of determinant form, that is ax, ay, az, dou by dou x, dou by dou y, dou by dou z of hx, hy, hz. So the equations, determinant equation, we know that we'll write the equations of the form ax into keeping that row and column aside, and remaining elements will write it as ax into dou h z by dou y minus dou by dou z of hy. Similarly for ay and az. So we'll commonly write the term in terms of plus. So ax, ay can be kept plus by interchanging the two components. So commonly we can write this equation and comparing that with the Maxwell's equation of del cross H equal to j omega epsilon into E into E. Into E is the electric field intensity in the direction of ax, ay and az. So it can be written like this: ax into ex plus ay into ey plus az into ez. So the same thing should be done for after comparing the components, writing the equations as 4.1, numbering it as 4.1, and similar thing should be done for del cross E. So del cross E is ax, ay, az, dou by dou y, dou by dou z, h, ex, ey, ez. So that thing can be written in terms of ax, ay and az. Similar thing for del cross E. We'll compare that with the basic equation, Maxwell's equation, and we'll write the component in terms of hx, hy and hz. So the two set of equations 4.1 and 4.2 is being very important for wave equation. And the next one is the wave equation can be given by in the second order form, that is del cross E equal to gamma square E and del cross H is equal to gamma square H. Where gamma is the propagation constant, it has to be considered in terms of sigma and omega and epsilon. So it is gamma is equal to sigma plus j omega epsilon into j omega mu. So del cross E can be written as in terms of if sigma equal to 0 for non-conducting medium, can be written as del cross E equal to minus omega square mu into epsilon into E. So similarly del cross H is equal to minus omega square mu into epsilon into H. So I'll get the two equations in terms of that is del cross E is del square E is dou square E by dou x square plus dou square E by dou y square plus dou square E by dou z square equal to minus omega square mu into epsilon into E. Similarly for H, del cross H is equal to del square H is equal to dou square H by dou x square plus dou square H by dou y square plus dou square H by dou z square equal to minus omega square mu into epsilon into H. So this set of equation is named as 4.3. So derived first one, we will just review whatever we studied till now. So we have written the equation for del cross H and then del cross E, and compared that with the basic Maxwell's equation, and written the terms by means of the comparison, the coefficients of both the equations. And then for the second order wave equations, del square E and del square H we have written. and we have explained what is propagation constant and how it can be written, and for the non-conducting medium sigma equal to 0. So the second part of the wave equation begins now, where gamma is the propagation constant, that is gamma is equal to sigma plus j beta, sigma or alpha, we can call it as alpha also, that is attenuation constant. If attenuation constant is that is the real part, and suppose beta is also 0, alpha is sigma or alpha equal to 0 for a non-conducting medium, that is without attenuation, and beta equal to 0, here is no wave motion, that is only the exponential decrease will happens with respect to the amplitude. So we know that the alpha or sigma attenuation constant reflects the waveform variation with respect to the amplitude, and beta will reflect the variations in terms of the movement of the waveform phase constant. Therefore, if h by any of the component which can be taken only in the direction of z direction, we can write the components of hy and hx like this, that is hy equal to the amplitude of that hy whole power 0 into e power gamma z minus gamma z, because we have a decrease in amplitude compared to the initial stage. So the first derivative of this equation becomes dou h y by dou in terms of z direction. So dou z equal to minus gamma into hy power 0 into e power gamma z. So same thing as hy power 0 e power minus gamma z is hy here. So dou h y by dou z is equal to minus gamma into hy. Similarly, we can write it for dou hy by dou z, hy and hx. So hx we can just replace hy by hx. And similarly for ey, we are writing the equation ey whole power 0 e power minus gamma z. So that is with respect to the we do the derivation. So we get dou ex by dou x and dou ex by dou z. The derivative with respect to y is 0. So keeping all these in mind and substituting all these equations, that is we have found the equation for dou hy by dou z and dou h is x by dou z, dou ey by dou z and dou ey by dou z, and the derivative with respect to y direction is 0. So substituting all these in 4.1, 4.2, 4.3, so we get the same set of equations in terms of gamma. We get 4.4 and 4.5. 4.4 is in terms of h and 4.5 is in terms of e. So the whole thing can be written in terms of dou square e by dou x square plus dou square e by dou y square is 0, and dou square e by dou z square becomes gamma square e. So substituting all these things, and we get another set of equation 4.6, where dou square e by dou x square equal to gamma square e, and dou square y by dou square h by dou x square equal to gamma square h. So writing this, and to solve for the equations gamma, that is hy, hx, hy, ex and ey, we have a set of equations in terms of hy, hx and hy. We have to solve for hy and hx, similarly ey and ex. Just by taking the equations and adding or subtracting it, we get the terms for hx to be minus gamma into ex by ey by j omega mu, and from that we will substitute it in the case of ey. Substitute it in the case of ey, hx, so we can substitute it in the case of ey. So we get hx term, we get a whole equation in terms of hx, that is hx equal to minus gamma by j omega mu into minus 1 by j omega epsilon into gamma into hx plus dou hx by dou x, dou hy by dou hz by dou x. So same thing for if we are keeping it for gamma by j omega mu, that is taking j omega epsilon outside, so we get omega square mu epsilon. And similarly hx, if you are taking it as common, we get the term like this. And finally hx is equal to minus gamma by omega square mu epsilon plus gamma square into dou h z by dou x. So this denominator can be kept as h square, where h square equal to gamma square plus omega square mu epsilon. To solve for hy, this is for hx, and similar things should be done for hy. So to solve for hy, we have gamma into ex plus dou ex by dou x equal to j omega mu into hy. That is, we are taking the same set of equation previous cases. This equation we are taking, second equation we are taking it, gamma into ex plus dou ex by dou x equal to j omega mu into hy. That is, we are taking all the terms, since all are being minus, we can take all the terms to be plus. So now what comes is dou hy equal to, we have derived dou hy equal to j omega epsilon into ex. So substituting all these two with the above equations, from the above equations we get hy is equal to j omega epsilon by gamma into ex. So substituting hy in case of ex, as like the previous case, we have derived this case, we have derived ey and substituted in the hx. So then we get the equation in terms of all in terms of hx, and we derive the equation for hx. Similarly, here what we do was we derive it for hy and substitute it in the ex equation. So we get the hy terms, and after simplification, taking the hy term common, and after simplification of it, hy we get as like the previous case hx, we get the hy term. To solve for ex and ey, the similar procedure should be done. To solve for, here we found hx and hy. Similar thing should be done for ex and ey. That is taking the first equation and then substituting hy in terms of ex in the both side equation, and we get 1 in terms of ex, the whole term in terms of ex, and we take the ex as common and keeping ex on one side and remaining terms on the other side. And similarly ey, the second set of equation, we can take it and substituting that in the previous equations, and we get the equations for ey, ex, hx and hy. So the solution of this and along with the set of equations will give you the, or called as the wave equations between the two